So good morning students. So 1 minute. Thank you. So good morning. So it is chemical bonding and molecular structure. So that's what we were discussing, right? So this particular topic we were discussing about. Now can any one of you tell me, or you can send the message, which topic madam is taking in same this one, chemical bonding, which concept madam is teaching now? Pooja, yes, limitations of octet theory, that's what we have discussed. At the same time I want which topic madam is taking. So limitations, yes, we have discussed in the last class related to limitations of octet theory. Yes, very good. So that's what we were discussing about. Okay. Hybridization. Fine. Thank you. So hybridization, up to that I have to finish it off. So limitations of octet theory we were talking about. Fine. So hagadre, when I am talking about limitations of octet theory, which are those limitations? So we have the compounds. There is the existence of the compounds which are having more or less than 8 electrons, where elements will be having more or less than 8 electrons. Even those compounds or molecules, still they are existing. So that is one of the limitations of octet theory. So what else? Yes, good morning everyone. Okay, so what else? That is one thing, compounds more or less than 8 electrons, they are existing. That is one of the limitations. Then we have the compounds. We have the compounds of inert gases. We have the compounds of inert gases. Yes, Dikshit. Good morning, Appa. So that's where we have the compounds of inert gases. Right? So that also existing. Now, same time, octet theory does not talk about shape and energy. Shape and energy of the compounds or molecules. So that's where these are the limitations of octet theory. Okay? So these are the limitations of octet theory. That's what we have discussed in the last class. Then along with that, already someone had written, even we have discussed about formal charge. Even we have discussed about the formal charge. Now when I am talking about formal charge, we have discussed by taking the help of ozone. We have discussed by taking the help of the ozone. So that's where we have the formal charge. Another important concept. Formal charge. Hagadre, when I am talking about formal charge, so formal charge is equal to, we have an equation. I will use Fc as the short form for formal charge. But in the exam you should write formal charge. Complete this one only. Okay? Fine? Yes. Yes, Pooja and Gannavi. Yes, I am going to discuss about the equation. So formal charge is equal to total number of valence electrons present in that element. Total number of valence electrons present in that element minus total number of unbonded electrons, or you can simply write it as lone electrons. We can simply write it as lone electrons. Okay, then minus total number of bonded electrons divided by 2. Total number of bonded electrons divided by 2. So that's where we have the equations for the formal charge. Same thing, we can write it in terms of lone pair also. What I mean to tell here is total number of valence electron minus total number of non-bonded or unbonded lone pair of electron minus total number of lone bonded electrons divided by 2. So pairs, then you have to talk about the pairs. But this will be easy. Unbonded electrons and total number of bonded electrons. This is with respect to formal charge, which we have discussed in the last class. All of you have understood? Fine. So that's what related to formal charge. We have taken the example of ozone. Okay. So we will move to the next one. Next one is with related to features of chemical bonds. What are those features or parameters? Okay. So we are going to discuss about some of the parameters related to bonds or chemical bonds. Okay. So that's what we are going to discuss. In that first one, I am going to talk about bond length. One of the parameters. Now, all of us we know that bond length will be distance between the nucleus, or I can tell it is the internuclear distance. Bond length is nothing but internuclear distance. It is the internuclear distance. So what do you mean by internuclear distance? We will imagine this is one atom, this is another atom, and that's where they have the bonding with each other. Now internuclear distance means this is the one, and whatever length is there, that will be considered as bond length involved in this case. That will be considered as bond length involved in this case. So therefore it is called as internuclear distance, because in a chemical bonding naturally there will be existence of two elements or more than two elements. For a particular bond it will be two elements. So in that case, when I am talking about two elements, naturally there should be presence of two nucleus. So one nucleus belongs to one element and another nucleus belongs to another element. So that's where we have the internuclear distance. That will be considered as a bond length. That is related to covalent bonds. If I am talking about an interaction where no covalent bond, then it will be van der Waals length or van der Waals interaction. So that will be different, which is applicable for inert gases because they will be present in monoatomic state. But we will focus on covalent bonds. So that's where we have the bond length. It is the internuclear distance. Bond length is the internuclear distance of the atoms or elements involved in the bonding. Okay, so that will be considered as bond length. Now I will take the example. If I take the example of carbon with a single bond length it's not an exact value. Bond length will be somewhere around 150 picometer. Since it will be very, very small, so we have to make meter into a smallest one, that is picometer. Okay, so 150 picometer. Now if I take double bond between the carbon, then it will be somewhere around 130 picometer. Somewhere around 130 picometer, approximate values it is. Now if I take triple bond, then I will consider this one as approximately 120 picometers. So 120 picometers. All of you have understood? So that's where we have the internuclear distance. So carbon with single bond 150 picometer approximately. Carbon double bond approximately it will be 130 picometer, and carbon triple bond it will be 120 picometer approximately. Okay, so hagadre by this example we can find that since it is a length, that is distance, therefore the unit should be meter or its derivatives. It should be meter or its derivative. For example, if I take angstrom, that is also derivative of meter only. 10 to the power of minus 10 meter, right? Angstrom means. Same way, we have the picometer. So what I mean to tell here is, bond length with respect to single bond, double bond and triple bond. What we can observe? What is happening to the bond length? Can you observe the table? What is happening? Can you observe the board? Can you tell me what you are observing? Single bond, double bond and triple bond. Whether it is increasing or it's decreasing, bond length. Any one of you? Whether it is increasing or it's decreasing. Okay. So Stephen is writing it's decreasing, but Ganevish has written increasing. Please, Ganevi, I am not talking about number of bonds. I am talking about the bond length. Okay? So therefore, as Shuchita, she has written yes. As the number of bonding will increase, bond length is getting decreasing. So don't get confused. I am not talking about number of bonds. I am talking about the bond length. So based on that I can tell that bond length of carbon single bond will be higher compared to carbon double bond, and bond length of carbon double bond will be higher compared to triple bond. That is with respect to bond length. If I take the number of bonds, yes, number of bond is 1 here, which is less than that of double bond, which is less than that of the triple bond, no doubt. So that means number of bonds and bond length, they are inversely related to each other. Or number of interaction between an element, as it increases, bond length is getting decreasing. All of you have understood? Number of interaction increases, what will happen to bond length? Bond length is also going to decrease. That means they are inversely related to each other. Any doubts in this? This is related to bond length. Any doubts? If you have any doubts, you can ask. So what do you mean by bond length? Bond length is the internuclear distance between the two atoms which are involved in the interaction or which are involved in the bonding. So that's where we have the bond length of that particular interaction. Okay. Now what is happening to the bond length with respect to number of interaction? As the number of interaction increases, bond length is going to decrease. Fine. Okay. So hagadre we will move to the next one. Next parameter. So next parameter is related to bond enthalpy. Next parameter will be bond enthalpy. Now, like ionization enthalpy and all, we have the bond enthalpy. So what do you mean by bond enthalpy? It is the amount of energy. It is the amount of energy utilized or required. Amount of energy required to break the bond. To break the bond. So that's where we have the bond enthalpy. Or I can tell that it is amount of energy utilized to separate the element involved in a chemical bonding in its gaseous state. All of you have understood? It is the amount of energy required to separate the elements which are involved in a chemical bonding in their gaseous state. That can be the definition of bond enthalpy. That can be the definition of bond enthalpy. All of you have understood? Fine? No doubts, right? Now, for example, I have the carbon-carbon single bond. I have the carbon-carbon single bond. Now, to break this particular bond, I may require some amount of energy. Once again, I will write approximate value. It can be somewhere around 100 kilocalories per mole. 100 kilocalories per mole, approximate, nearby values. They are not exact values. Now at the same time, if I have the carbon-carbon double bond, what do you think? Whether the value should increase or it should decrease? The value should increase or the value should decrease? Guessing, increase or decrease? Carbon-carbon single bond, approximately 100 kilocalories per mole. Unit for bond enthalpy can be kilojoules per mole or kilocalories per mole. Anything is fine. It can be kilojoules per mole or kilocalories per mole. Yes, as you people have written, yes, it should increase. It can be somewhere around 140 kilocalories per mole. Once again, I will tell, it's not exact value, please. No need to remember the values and all. Now, carbon-carbon triple bond, it will be somewhere around 180 kilocalories per mole. Okay? Now, bond enthalpy, since enthalpy, that is heat, that is energy. So, therefore, unit should be kilojoules or kilocalories. So, kilojoules per mole or kilocalories per mole. The value will change. If you want to convert it into kilojoules, value will change. Okay, anyway, so that's fine. But we are not bothered about exact values. But I want you to understand what is happening to those values. All of us, we can see that there is an increase in the bond enthalpy values. There is an increase in the bond enthalpy values. Now, if you recollect, 2 minutes back we have discussed about bond length. Now, can you tell me the relation between bond length and bond enthalpy? Just mention that whether it is inversely related or whether it is directly related. That's all. Just mention inversely or directly. So, whether bond length and bond enthalpy, what is that relation? Yes, I will give. I will give. What is that? They are, Suchita, it should be inversely. As Stephen has written, yes, it should be inversely related. They are not directly related. Ganavi, bond length and bond enthalpy, they are not directly related. They are inversely related. As the bond length is decreasing, see, for example, if I take the bond length somewhere around 120 picometer, right? Same way here, it was 130 picometer. And here it was somewhere around 150 picometer. So what is happening? Bond length, it is getting decreasing. it's getting decreasing, but bond enthalpy it is getting increasing. This is important for your competitive exams and all. Okay, so naturally bond length I will take it as BL, bond length, and bond enthalpy I will consider this one as BE. Okay, not Bachelor of Engineering. Okay, now so BL is inversely proportional to bond enthalpy. Fine. So that's what we can find the relation. That's what we can find the relation. Fine. For example, if I want to take another example, a beautiful example, a common one which we observe in the nature is nitrogen. If I take nitrogen molecule will be present in the nature with a triple bond. Okay, so nitrogen molecule, all of us we have studied in our Lewis symbol, right? Or in that way we have discussed about nitrogen which are having triple bond with each other. So that's where we have the nitrogen molecule. Okay, now to break this particular bond, to break the bond present between two nitrogen with triple bond, it demands very high amount of energy. It can be somewhere around 250 kilocalories per mole. To break this particular bond, it demands 250 kilocalories per mole. Pretty high amount of energy is required. Now, biology students will be knowing, or all of you have studied in your 10th standard, that in the atmosphere, which particular gas will be of higher concentration? Can any one of you tell me? In the atmosphere, which particular gas will be at high concentration? Whether it is oxygen or nitrogen, which will be present at high level concentration in the atmosphere? Okay, still Stephen has written oxygen. Shuchita, no, you people are wrong. It's not oxygen. It is the nitrogen which is present at high amount. Okay, so somewhere around 72%. It will be present somewhere, or 78%, somewhere around 78%. And if you take the oxygen, it is hardly 22%. It is hardly 22%. Oxygen is less. Now all of us, we are feeling bad, right? Oh God, we are respiration, we require oxygen. We would have got oxygen at 78%. Why the hell nitrogen is there? That's what we used to feel, right? As a student, I used to feel the same thing. Why nitrogen such a high amount? Why not oxygen? Then there is no requirement of yoga and all, because enough oxygen is there. All of us would have lived happily, but that is wrong. If oxygen would have been in a reverse direction, nitrogen became 22, oxygen 78, our lifespan would have been decreased, because oxygen is more reactive compared to nitrogen. Okay, oxygen is more reactive compared to nitrogen. Therefore, nitrogen molecule will be considered as azote. That means without life. So nitrogen is acting as a diluent for the oxygen. Please remember, without nitrogen we cannot imagine this atmosphere. Don't think that oxygen, if it is too high, we will be living happily. No. Oxygen is reactive. It can give rise to radical formation, reactive oxygen species, ROS, which is one of the factor for the most of the disease in our body. So therefore, nature, such a beautifully designed the nature has designed this atmosphere so beautifully, where we can live 70 years, 80 years, right? So that is because of this molecule. And because of its triple bond, that's why they are less reactive. Because of the presence of the triple bond, therefore they are very less reactive. I am not telling that they are inert gases. No. But they are very less reactive. ಈಗ ಹಾಸ್ಪಿಟಲಿಗೆ ಹೋಗ್ತಿರಲ್ವಾ, they will put oxygen cylinder, right? So don't think that it will be 100% oxygen. No. It will be diluted by nitrogen or helium, inert gas. They will use to dilute the oxygen. 100% oxygen cannot be inhaled directly. It will lead to further problem with respect to our system. All of you have understood? So that's where, as there is a number of bonding increases, it's going to increase the bond energy. It's going to decrease the bond length. Okay? All of you have understood? So therefore, always we should be appreciate this nature. So beautifully it is designed, right? But we the humans, we are spoiling this one by making some of the unwanted gaseous molecule concentration, we are increasing. Anyway, that's another concept which you are going to study in your environmental chemistry, but don't see this one as your subject. You should think this one as a real concern, okay? Because we have to live. We have to live on this earth, okay? So, shall I move to the next one? Any doubt? What is that relation between bond length and bond energy? Bond length and bond energy, they are inversely related to each other. Fine? Shall I move to the next one? Okay? So next one will be with respect to, okay fine. Next one will be with respect to bond order. Next one will be with respect to bond order. Hagadre, when I am talking about bond order, okay, I will give an example, now you can tell. So when it comes to carbon-carbon, single bond, carbon-carbon double bond, carbon-carbon triple bond. So bond order for this one will be 1. Bond order for this one will be 2. Bond order for this one will be 3. So hagadre, what do you mean by bond order? Bond order is nothing but total number of bondings. Bond order is nothing but total number of interactions present between the elements. Got my point? So what do you mean by bond order? It is the number. It is the total number of interactions. Total number of interactions between the elements. Total number of interactions between the elements. Or interaction, or you can use the total number of bondings present between the elements. So that's where we have the bond order. Okay? So in the nature, nitrogen will be having bond order of 3. So bond length is directly proportional to bond order? No. They are inversely proportional, because as the bond order increases, bond length is going to decrease. So I will make a statement. So BO stands for bond order. So it will be directly proportional to bond energy. It will be directly proportional to bond energy, and both of them, they are inversely proportional to bond length. All of you have understood? So what is BO here? BO means bond order. BE means bond energy, and BL means bond length. Not bond length, sir, bond enthalpy. So that's what? Bond length, okay, bond enthalpy, yes, they are directly related. Yes, you are right. So bond order and bond enthalpy, they are directly related, but both of them, they are inversely related to bond length. Fine? All of you have understood? Okay? Hagadre, if I take the example, I will write one of them. All of you have understood this one? Shall I remove this? Fine? So hagadre, if that is the case, I will give one example over here. 2 elements I will write, I think, which is there from your textbook only. That is nitrogen and carbon monoxide. nitrogen and carbon monoxide. What is the bond order for these elements? What are the bond orders for these elements? Nitrogen and carbon monoxide. Nitrogen and carbon monoxide. What will be the bond order for this? Anyone? You can just mention the number. What is the bond order for nitrogen and carbon monoxide? Yes, Pooja, you are absolutely right. It will be 3. Both of them, they are having bond order of 3. That's where carbon monoxide and nitrogen, both of them, they are having the bond order of 3. Now can you calculate what is the total valence electron in these molecules? What is the total electrons? Can you calculate? What is the total number of valence electrons in these elements? Can you calculate? Just send me the number. Total number of valence electron with respect to nitrogen molecule and with respect to carbon monoxide molecule. Rohan, how it can be 4? Say for example, if you take nitrogen, one nitrogen 5, another nitrogen 5, total it should be 10 electrons. Total it should be 10 electrons. Okay, people are getting confused. Now you might be understood. So I am talking about total number of valence electron in these elements in a molecule. So nitrogen 5, total 10 electrons. What about this one? Carbon monoxide. What is the total number of valence electrons with respect to carbon monoxide? Yes, Shuchita, absolutely correct. Here also it is 10 electrons. Here also it is 10. Oxygen 6, carbon 4. Total 10 electrons. Right? I am talking only about the valence electrons. If that is the case, I can tell that they can be an example for isoelectronic species or isoelectronic molecules because they have the total number of electrons same. So I can consider them as isoelectronic molecules. What do you mean by isoelectronic molecules? We have discussed. So isoelectronic species means these are the group of elements which will be having same number of electrons. Okay, so that's where we have the molecules. Any doubts in this? If you take total electron also it will be same, but it will be 14 electrons. So 7, 14 electrons, and 8 and 6, once again 14 electrons. Anything is fine. If I take only total valence electron, it will be 10 electrons. If I take total number of electrons, then also it will be 14. It will be same. So therefore it will be isoelectronic molecules. Okay. So hagadre, can you do it for the molecules like fluorine and peroxides? This is nothing but peroxide, not oxygen. This is not an oxygen, it is a peroxide. Can you do it for this one? These two, one is an ionic molecule and another one is a molecule. One is fluorine molecule and another one is peroxide molecule. Can you calculate? What is the bond order? So bond order here it will be 1 because fluorine with single bond, even oxygen will be with single bond. They don't have the double bond. So don't get confused. When I am writing oxygen molecule like this, I am talking about oxygen having double bond. That is the one which I am going to use during respiration. We are inhaling that one, not this one. This is a peroxide, a reactive molecule. Okay, so that is oxygen molecule. So when I am talking about peroxide, they will be having single bond, not the double bond. So therefore, both of them will be having bond order which will be 1. Now what about total number of electrons? What will be the total number of electrons? Anyone? What will be the total number of electron with respect to fluorine and with respect to peroxides? Anyone? So total number of electrons will be, in this case, 9 and 9. Total it will be 18 electrons. So in this case, we have extra electrons, right? Minus 2. So extra 2 electrons are there. So oxygen atomic number is 8. But 1 extra electron, 9. Another oxygen atomic number is 8. Another 1 extra electron, therefore 9. So therefore total number of electron will be same. So that is 18 electrons. So that is 18 electrons. All of you have understood? Any doubts? If you have any doubts, you can ask. Okay? If I take total valence electron, then also it will be same. Total valence electron if I consider, here it will be 7 and 7, that is 14 electron. Here also it will be 7 and 7, 14 electron. Actually, total valence electron for oxygen is 6, but 1 extra electron. Therefore, 7 and 7, once again 14 electron. So total valence electron same. So total number of electrons will be same. So naturally, when total electron will be same, valence electron automatically it will become same. Okay? So therefore, both of them they are example for isoelectronic molecules or isoelectronic species. So what is that conclusion you can take from this particular example? The conclusion here is, with respect to isoelectronic species, bond order will be same. Or I can tell for bond order will be same for the isoelectronic species. They cannot have the different bond orders. All of you have understood? So therefore by these examples I can tell that bond order for a isoelectronic species, will be same. Although the molecules will be different, but they will be having bond order same. Fine? Any doubts with regard to this one? Okay, Rohan. So in that case, sir, we need to consider the valence electron. Shuchita, whether you to consider valence electron or whether you consider total electron, both are related to each other. When total electron will be same, then valence electron automatically it will become same. But if I consider only valence electron, then chlorine, fluorine, they cannot be considered as the isoelectronic species. Because although they have the same valence electron, but they are not isoelectronic species. Okay? Whether I got the point? So better to go with the total number of electrons. Then only we can tell them as isoelectronic molecules. total number of electron. But if I consider only valence electron, then in that case Cl, chlorine and fluorine, whether they are isoelectronic? No. But they have the same number of valence electron. Okay? So that's where we have the concept. Now the last one is bond angle. The last one is bond angle. Naturally, in the name itself it is there. It is the angle formed between the two bonds in a molecule. This is the angle between the two bonds in a molecule or a compound, whatever it is. Okay? For example, if I take nitrogen, there is no question of bond angle. For nitrogen, there is no question of bond angle because only two elements are involved. No question of bond angle, right? But if I take water, since two separate bonds are present, now we can apply the bond angle concept, where in this case the bond angle will be somewhere around 104.5 degree. So 104.5 degree. All of you have understood? When I am talking about bond angle, there should be involvement of more than two elements. Because when there is more than two elements, then only two separate bond will be formed. Otherwise, with only two elements, bond angle concept cannot be applicable. All of you have understood? Any doubts? Okay? And if that is the case, if I consider water as an example, if I want to find out what is the bond enthalpy, sir, for carbon dioxide, yes, carbon dioxide, it will be 180 degree. For carbon dioxide, it will be 180 degree. It's a linear molecule. Oh, sorry, Celsius I'm writing. So it is a linear molecule, 180 degree. Bond angle will be 180 degree. So three elements are there. Bond angle can be applicable. Okay? So now, if I want to see this molecule, if someone asks you, what is the bond enthalpy for the water molecule? Now you will get confused. Raghavendra sir has told us bond enthalpy means breaking of a particular bond. Then why the hell here two bonds are there? How to talk about bond enthalpy for a water? Then you should take the average. We should take the average bond enthalpy of these two bonds. Okay? Say for example, if I take the bond enthalpy for water, I will consider this one as 1 and I will consider this one as bond 2. Now what I have to do is bond enthalpy for 1, okay, bond enthalpy for 1, bond enthalpy for 2 divided by 2. That will be giving the average bond enthalpy. That will give the average bond enthalpy. That's how we should give the bond enthalpy for a given compound where more than one elements are involved. All of you have understood? So that's where we are going to get the average bond enthalpy or mean bond enthalpy. Average or mean bond enthalpy. If I have 3 bonds, then divided by 3. If I am having 4 bonds, then divided by 4. I am talking about multiple different bonds. Don't consider this one as a 3 different bonds. No. These are the 3 interactions happening between the 2 elements. So this cannot be considered as bond 1, bond 2, bond 3. No. But here, bond 1 and bond 2. Here also bond 1, bond 2. So like that we have to consider average bond enthalpy. All of you have understood? Any doubts? Sir, how to calculate the bond angle? Okay. Actually, that's not there for a paper, but it's a good question. When I am talking about bond angle, it cannot be calculated as it is. We have to go with the VSEPR theory. We have to consider the hybridization. Based on that, what is the amount of electrons left over? Based on that, we have to calculate. For that, we should know what will be the shape of the molecule. What will be the shape of the molecule, which you are going to study in VSEPR theory. Okay, that will come. It's a good question actually. Fine. But for that, we should know what is hybridization and what is the shape of the molecule. Based on that, we can tell what will be the bond angle. Fine. Any other doubts? But it's a good question. Rohan had asked something. Even for methane, there is a bond angle. No, sir. Somewhere. Yes. For methane also it is there. Because it is a tetrahedral in shape. So based on that, that is the bond angle. So what I mean to tell you is, in the nature, these elements, they want to stay as far from each other. They don't want to come close to each other. Okay? So based on that, they will be having different shapes. And therefore, they will be having different bond angle. Okay? All of you have understood? Anyway, in VSEPR theory, even I will talk about bond angle for different shapes. Don't worry. But this much you have understood? So, we will move to the next one. But try to remember relation between bond order, bond length and bond enthalpy. Try to remember that. Fine? So, hagadre we will move to the next one. That is resonance. That is related to resonance in detail. For resonance, we are not going to discuss here. We are going to discuss that one with respect to your organic chemistry. Sir, bond angle is directly related to or inversely related? It's nothing relation, Manjunath. Bond angle is related to shape of the molecule. Okay, it's related to shape of the molecule. It's not have any impact with respect to the bond enthalpy. Fine? It's related to shape of the molecule, bond angle. Okay, na? So that's where we are going to discuss about resonance. I will give a brief view about the resonance, but in detail with respect to organic chemistry, we are going to discuss this one in second part of your chemistry. Fine? So, if I take the ozone, all of us we know that ozone will be having this type of structure. That's what we thought. We thought that there will be presence of double bond between oxygen 1 and 2, and there will be presence of single bond between oxygen 2 and 3. That's what we thought. So why you are telling like this? We thought. That's what you have written. That's what it will be coming to your mind, right? But otherwise, I can write the another form of oxygen, that is ozone. Okay? So 1, 2, 3. This is also fine. This is also fine. Now we got the confused. So what is this? In first case you are showing double bond between oxygen 1 and 2. In second case you are showing double bond between 2 and 3. How it's possible? Right? So that's where the resonance comes. So this will be considered as canonical structure. This will be considered as canonical forms. Canonical form 1 and canonical form 2. Okay? Canonical structure in reality, listen to me carefully. Canonical structure in reality does not exist. It's our imaginary structure. If I write the structure of ozone, if I write first one, that is also correct. If I write the second one, that is also correct. If both are correct, how come it will be a ozone molecule? That's what I am telling. So that's why they are canonical forms. They are the imaginary forms. which does not exist in reality. Theoretically, they are present. Practically, they are not present. Practically, ozone will be present with hybrid form, where we have the oxygen, 3 oxygen, which will be having partial double bond between these. All of them, they are having same type of bonding. This is called as hybrid, resonance hybrid form. And this hybrid form is the one ozone is existing. In this hybrid form is the one ozone molecule is existing. All of you have understood? If I have taken the example of ozone, canonical form 1, canonical form 2. That's what in reality we used to write. Therefore, I told theoretically they might be correct, but in reality, that is practically, they are not existing. Practically, it is the hybrid form of structure which is existing, which is called as resonance hybrid. That structure is called as resonance hybrid. So, this is the one which is present in reality. On what basis we are telling this one, sir? The simple concept here is, all of us we know that since bond length is double bond here and since single bond here is, so bond length should be higher, right? And bond length should be lesser, right? Single bond, double bond. Based on that, we can tell that wherever double bond is there, bond length should be higher. Wherever single bond is there, bond length should be reverse. So here bond length should be lesser. Bond length should be lesser. And wherever single bond is there, bond length should be higher. That's what we are concluding, right? By seeing the bond order. So bond order 2, bond order 1. So therefore bond length higher, bond length lesser. That's what we will conclude. But on the other side, it will be reverse. On the right hand side, bond length will be less, and on the left hand side, bond length will be high. Exactly opposite. That's what we will have the canonical structure, right? So according to this, bond length will be lesser and bond length will be higher. That's what we can observe. Adare. Listen to me carefully. But in reality, both the bond length, it is same. They don't have the different values. Both the bond lengths are same. They don't have the different values. That is in reality with respect to the hybrid form of the ozone or resonance hybrid structure of the ozone, where bond length are same. Where bond lengths are same. They are not different at all. Now the speciality here is, and this bond length will be between ozone double bond and oxygen single bond. They are between these values. Whether all of you have understood? If I see the bond length here, whatever bond length we expect for oxygen double bond and whatever bond length we expect for oxygen single bond, the value here will be exactly between these two values. They are not showing the value of double bond length, they are not showing the value of single bond length. They are showing the value which is somewhere between double bond length and single bond length. So therefore it is called as partial double bond character. Therefore this feature is called as partial double bond character. Partial double bond character. All of you have understood? So that's where we have the partial double bond character. On what basis we are telling there is a partial double bond? In reality that's not possible. Theoretically it is impossible. How can be a partial double bond can be present? Either it can be single bond, either it can be double bond or triple bond. No question of partial double bond. How it's possible? So that's what in reality it is happening. That's where resonance forms comes into picture. All of you have understood? Any doubts? On what basis we are telling partial double bond character? Because whatever bond lengths are present between 1 and 2 and 2 and 3, they are same. That is one thing. There is no difference. And along with that, if I see those values, they are exactly between double bond length and single bond length. They are in the center of these two values. They are not going to this value also. They are not showing this value also. So therefore, it is called as partial double bond character. Therefore, it will tell that it's partial double bond character. Okay. So this is an example for resonance features. Okay. This is an example for resonance feature. Now, when it comes to resonance, it will provide the stability. It will provide the stability. That's what people will tell. It will provide the stability because whatever hybrid form will be there, it will be of lower energy. Whatever hybrid form is there, it will be of lower energy. Okay? Rohan, why you are telling thank you? You thought class is over? Huh? Okay, now. So that's where we have the resonance forms, where resonance hybrid will be having lower energy. So therefore molecule will have the stability compared to their canonical forms. But when you are writing the ozone structure, we will be writing either canonical form 1 or canonical form 2 to make it easier. Okay? All of you have understood? Anyway, in detail with respect to resonance, we are going to discuss in organic chemistry. Any doubts? Okay? So anyway, I will stop here. Rohan has told already thank you. Okay, I am kidding. Okay? So anyway, I will stop here. Any doubts? Okay. So when it comes to the definition for resonance, these are the conditions. Why I have not given definition here? Because in organic chemistry, when we explain in detail, then you will understand. Anyway, so these are the conditions where molecules cannot be written or cannot be explained, cannot be written in one form, and there will be existence of hybrid form, that is called as resonance. Okay. Anyway, this is related to whatever I have explained. Based on that I have given, but proper explanation you will understand when it comes to organic chemistry. Okay. So that's where we have the resonance, where molecule can be written in more than one form. See, for example, if I write oxygen molecule, I cannot write more than one form, its structure. It is only one. That is the only thing. I cannot write oxygen molecule in some other form. Nothing. It's not possible. Same logic. If I want to write the nitrogen, only one form. There is no question of another form. But when I am writing ozone, I can write it in two forms. Right? So when I am talking about carbonate, when I am talking about benzene, all of them, they can be written in more than one form. So that's where resonance will come into the picture, where a molecule can be written with more than one form. That's where we have the resonance. Okay? Anyway, I'll stop here. So on Monday, we are going to continue with the class. So by that time, you can go through the textbook and check sheet, and please remember 2 classes are happening for this topic, so you should be reading, you should be updating yourself. Okay? Yes, Rakesh, we'll meet on Monday. Thank you. Take care. Thank you. Bye. Please take care.